time travel is already weird. But what if something could exist without ever being created? This is the Bootstrap Paradox, a mind-breaking paradox where something seems to appear out of nowhere, with no origin at all. Imagine you're a scientist, and one day you receive a mysterious package. Inside, you find a book on advanced physics, full of theories no one has discovered yet. You study it, publish the ideas as your own, and over the years the world advances because of your discoveries. Decades later, you're old and decide to pass the knowledge on. So, you take the book, travel back in time, and give it to your younger self. But wait, where did the book originally come from? You didn't write it. You received it from your older self. But your older self only had it because they got it from their younger self. The book has no point of creation. It simply loops through time, existing forever. Normally, everything must have a cause. A book must be written. An idea must come from somewhere. But in a bootstrap paradox, information or objects appear from nothing, never created, just eternally existing. And it's not just books. Imagine a composer who time travels to meet Beethoven and gives him a copy of his own symphonies. Beethoven then copies them down, and history records him as the composer. But if he only wrote them because he saw them in the future, who actually composed the music? While this sounds impossible, physics doesn't entirely rule it out. Some interpretations of time travel suggest that information loops could exist, as long as they remain self-consistent, meaning they don't contradict anything in the timeline. Even stranger, in quantum mechanics, there are cases where particles seem to influence themselves backwards in time, which some physicists argue might be a real-world version of a bootstrap paradox. If a bootstrap paradox can happen, then some things in reality might not have a true origin. What if some of our biggest ideas, mathematics, technology, even human consciousness, aren't discovered, but instead loop back into history from the future? And if so, how do we know what's truly real and what's just an echo of something that was never created in the first place? What if you could never die? Not because of medicine or technology, but because the laws of physics simply don't allow it. This is the paradox of quantum immortality, an idea so strange that, if true, it would mean that, from your own perspective, you will always experience survival, no matter what happens. It sounds impossible. But let's break it down. To understand this paradox, we need to look at the many worlds interpretation of quantum mechanics. In quantum physics, particles don't have definite states until they are measured. Before observation, they exist in a superposition, a blend of all possible outcomes. The many worlds theory proposes that every time a quantum event occurs, the universe doesn't choose just one outcome. It splits into multiple realities. Every possible event happens, but in separate universes. Now imagine that your survival is linked to a quantum event. Say, a device that measures the decay of a single radioactive atom. If the atom decays, the machine triggers, and you don't survive. If it doesn't decay, you live. According to many worlds, the universe splits. In one, you die. In the other, you live. But here's where things get strange. You can only be conscious in the universes where you survive. From your own perspective, no matter how improbable, you always experience the timeline where you continue living. This is quantum immortality. If this paradox is real, then it means that no matter what happens, whether it's an accident, an illness, or even extreme aging, your consciousness will only exist in the branches of reality where you remain alive. But immortality comes with a cost. Just because you survive doesn't mean you survive well. In some realities, you might be severely injured, in a coma, or even lose all cognitive function. But you'd still technically exist. And here's the real mind-bender. If quantum immortality is true, then for you, there is no such thing as death. You will never experience the moment of non-existence. Every time you come close, the universe finds a way to keep you going. Now, before you start testing this theory in dangerous ways, let's be clear. Quantum immortality relies entirely on the many worlds interpretation, which is still just a theory. Other interpretations of quantum mechanics, like the Copenhagen interpretation, suggest that reality doesn't split at all. Only one outcome actually occurs. And even if many worlds is true, we don't know if consciousness works this way. We don't know if there's something special about you that forces reality to always branch in your favor. So are you actually immortal? Probably not in any meaningful way. But if this paradox is real, then somewhere, in some universe, you are still alive, and you always will be. Imagine you're walking past a shallow pond and you see a small child drowning. No one else is around. You could wade in and save them easily, but your shoes would get ruined. Would you hesitate? Of course not. No reasonable person would let a child die just to save their shoes. That would be monstrous. But according to philosopher Peter Singer, this is exactly what most of us do, every single day. Singer argues that if it's wrong to let a child die right in front of you when saving them is easy, then it's also wrong to let a child die far away when saving them is just as easy. Right now, thousands of children die every day from causes that could be prevented with basic aid: clean water, food, medicine. And for the cost of a nice dinner or a new pair of shoes, you could save a real, living child's life. But most of us don't. We see charity as optional, not a moral obligation. But why? If distance doesn't change the moral weight of an action, then failing to donate to effective charities is functionally the same as walking past a drowning child and doing nothing. Here's where it gets disturbing. If Singer is right, then ordinary people who don't see themselves as bad, are actually actively allowing preventable deaths. And it doesn't stop at charity. Every luxury we indulge in, while others suffer, is a choice to prioritize our comfort over human lives. If that makes you uncomfortable, that's the point. Can this argument be escaped? Of course, people try to justify their inaction. Some say, "It's not my responsibility," or "I can't save everyone." But those arguments don't hold up. You weren't responsible for the drowning child either. But you'd still feel obligated to help. And sure, you can't save everyone. But that doesn't mean saving no one is justified. So, are we all evil? If Singer is right, then evil isn't just about doing harm. It's about failing to prevent it when you easily could. And if that's true, then most of us aren't just occasionally selfish. We are living daily proof that moral indifference is woven into the fabric of modern life. Imagine a ship, ancient, majestic, sailing across the sea. Over time, its wooden planks start to rot, so one by one, they are replaced. Eventually, after years of repairs, every single piece of the ship has been swapped out. Now, here's the question. Is it still the same ship? This is the Ship of Theseus Paradox, an ancient philosophical puzzle that forces us to ask, what makes something what it is? Let's break it down. If replacing one plank doesn't change the ship's identity, then replacing 10 planks shouldn't either. Neither should 100. But if you keep going, eventually, none of the original ship remains. So when did it stop being the original ship? After half the planks were replaced? The last piece? Or was it always the same ship, just with new materials? Now, let's make things weirder. Suppose someone gathers all the original planks and rebuilds the ship exactly as it was before. Now you have two ships, one made from new materials, one made from the old ones. So, which one is the real Ship of Theseus? This isn't just about boats, it's about identity. And it applies to everything. Take your body. Right now, your cells are dying and being replaced. In fact, every 7 to 10 years, almost all the cells in your body have been replaced. So, are you still the same person you were a decade ago? What about your mind? If your thoughts, memories, and personality evolve over time, are you still the same you? There are different ways to approach this paradox. One idea is that identity is tied to continuity. As long as the change happens gradually and the function remains the same, it's still the same thing. By this logic, the Ship of Theseus remains itself because it never stops being a ship. And you remain yourself because your consciousness flows continuously over time. Another idea is that identity depends on material, which would mean the rebuilt ship made from the original planks is the real one. But if that's true, then does that mean you aren't the same person you were 10 years ago, since your body's cells have changed? Or maybe identity isn't a fixed thing at all. Maybe it's just a label we use to make sense of an ever-changing reality. The Ship of Theseus isn't just a fun puzzle. It's a crack in the way we understand reality. It forces us to ask, what does it really mean for something to exist over time? And if we can't answer that, then how do we even define who we are? Time travel. It's one of the most fascinating ideas in science fiction, but if it were possible, it would create one of the most disturbing logical contradictions ever imagined. This is the grandfather paradox, a problem so bizarre that it might prove time travel to the past is completely impossible. Imagine you build a time machine and travel back in time. You go far enough back to when your grandfather was young, before he ever had children, and then, for whatever reason, you prevent him from meeting your grandmother. Maybe you even kill him. Now here's where reality starts to break down. If your grandfather never has children, that means your parents were never born. And if your parents were never born, then you were never born. But wait, if you were never born, then how did you travel back in time in the first place? You just erased your own existence, and yet you were still there to change history. This contradiction, the fact that you exist and don't exist at the same time, is what makes the grandfather paradox so mind-bending. In normal reality, cause and effect are simple. The past causes the present, and the present causes the future. But the grandfather paradox shatters this. By altering the past in a way that erases your existence, you create a loop that can't logically resolve itself. If you don't exist, you can't go back in time. But if you don't go back in time, your grandfather lives, and you do exist. This forms what's called an inconsistent causal loop, a timeline that contradicts itself, making reality unstable. So, does this paradox prove time travel is impossible? Maybe. But physicists have come up with some wild theories that could resolve it. One idea is the Novikov self-consistency principle. This suggests that the universe simply won't allow paradoxes. If you travel back in time, something will always prevent you from changing the past in a way that causes a contradiction. Maybe your gun jams or you change your mind at the last second. No matter what, events will always align so that history remains intact. Another possibility is the many worlds interpretation. This suggests that the moment you change the past, you create a new timeline. One where your grandfather never had children, but also one where the original you still exists in a separate universe. In this version, time travel doesn't rewrite history. It just creates a new history. If time travel to the past is possible, then either paradoxes are somehow prevented, or the universe splits into different timelines. Every time a paradox is created. But if neither of these solutions is correct, then the grandfather paradox might be the ultimate proof that traveling backward in time is fundamentally impossible. Either way, one thing is certain: time is far stranger than we ever imagined. What if everything you've ever experienced, your memories, your thoughts, your entire life, wasn't real? Not in the way you think, at least. What if you were living inside a simulation? This isn't just a sci-fi idea. It's a serious philosophical and scientific question. And the deeper you go, the more disturbing it gets. The simulation hypothesis suggests that what we call reality might actually be a highly advanced computer simulation, created by a more advanced civilization. If true, it means that everything, matter, energy, even your consciousness, could be nothing more than digital information running on an incomprehensibly powerful system. But here's the mind-breaking part. There's actually a strong argument for why this could be true. This idea was popularized by philosopher Nick Bostrom, who proposed a simple but terrifying probability problem. If human civilization continues advancing, we will eventually develop the ability to create hyper-realistic, simulated worlds, complete with conscious beings who don't know they're in a simulation. If it's possible to create one simulation, then an advanced civilization could create millions, maybe even billions of them. If most conscious beings exist inside simulations rather than the original reality, then statistically, we are probably in one right now. Think about it this way: if there are 1 trillion simulated worlds and only one real one, the odds that you're in the one real world are practically zero. If we are in a simulation, could we find evidence? Some scientists have suggested that certain oddities in physics, like the limitations of the speed of light or the quantization of spacetime, could be signs that reality is pixelated, like a digital program running at a fixed resolution. Others suggest that things like quantum mechanics, where particles don't settle into definite states until observed, could be an indication that reality renders itself on demand, just like a video game that only generates what's on the screen. But here's the part no one wants to think about. If we are in a simulation, who built it and why? Are we part of an experiment, a form of entertainment, a simulation running on some alien teenager's laptop? And perhaps most terrifying of all, what happens if they turn it off? If you really are in a simulation, does it change anything? After all, your experiences still feel real. Your emotions still feel real. And maybe that's all that matters. But if the simulation hypothesis is correct, then the reality you think you know is nothing more than a fragile illusion, one that could be erased in an instant. Tolerance sounds like a simple idea. If we allow people to express their beliefs, society becomes more open, fair, and peaceful. But what if tolerance itself contains a fatal flaw? One that, if taken to its extreme, actually destroys tolerance altogether. This is the paradox of tolerance, an idea first introduced by philosopher Karl Popper. And once you understand it, you'll never look at freedom the same way again. Here's the problem. If a society is completely tolerant, it must tolerate even the most intolerant ideas. But what happens when those intolerant ideas start gaining power? Let's say an open, tolerant society allows a movement that hates tolerance to spread unchecked. Over time, that movement grows stronger, using the society's own freedom to push for its destruction. Eventually, it reaches a point where it overthrows the very tolerance that allowed it to exist. The result? Tolerance is wiped out by tolerance itself. Popper argued that to maintain a tolerant society, we must be willing to intolerate intolerance. In other words, tolerance can't be absolute. At some point, a society must defend itself by refusing to tolerate ideas that would lead to its collapse. But here's where it gets tricky. Where do you draw the line? If a society suppresses intolerance too aggressively, it risks becoming intolerant itself, acting in ways that mirror the very forces it opposes. But if it does nothing, it risks being destroyed from within. This paradox isn't just a thought experiment. It applies to real-world issues like free speech, extremism, and censorship. Should hateful ideologies be given a platform in a free society? If we ban them, are we betraying the very freedom we claim to protect? Or is allowing them to spread just setting up the conditions for freedom's eventual downfall? The paradox of tolerance forces us to ask a disturbing question. Does true freedom require limits? And if so, then tolerance isn't just about allowing all voices. It's about knowing which ones could endanger the very idea of tolerance itself. Imagine you have a twin. One day, they board a spaceship and blast off into space at nearly the speed of light while you stay on Earth. Years later, they return, but something is wrong. Even though you were born at the exact same moment, your twin is now younger than you. Maybe much younger. This is the twin paradox, a bizarre consequence of Einstein's theory of relativity. It sounds like science fiction, but it's real, and it's already been tested. At its core, the twin paradox is about time dilation. The idea that time doesn't pass at the same rate for everyone. According to Einstein's special relativity, when something moves faster, time slows down for it relative to a stationary observer. So if your twin travels at near light speed, time, for them, slows down, while time for you on Earth stays the same. From your perspective, they experience time in slow motion. What feels like decades for you might feel like only a few years for them. So when they return, they are younger than you, as if they have traveled into the future. The twin paradox actually isn't a proper paradox. There are no contradictions, but the implications just kind of feel contradictory. Imagine things from the twins' perspective. They see you moving away from them at near light speed. So shouldn't your time slow down too? Shouldn't you both age slower than the other? It seems like a contradiction, but it isn't. The key is that the traveling twin changes reference frames when they turn around and come back. They experience acceleration and deceleration, while the twin on Earth stays in a single frame of reference. That acceleration breaks the symmetry, meaning the traveling twin really does age less. Yes, this isn't just theory. Scientists have tested time dilation using atomic clocks on fast-moving planes. The clocks that travel experience a tiny but measurable time lag compared to those that stayed on Earth. And with astronauts, the effect is real too. Cosmonaut Sergei Krikalev, who spent 803 days in orbit, aged about 1/50th of a second less than people on Earth. That might not sound like much, but if we could travel near the speed of light, the difference could be decades. The twin paradox isn't just about space travel. It's about what time really is. It means that time isn't a universal constant. It's flexible, stretching, and compressing based on how you move. So if you want to travel into the future, you don't need a time machine. You just need to go fast enough. Look up at the night sky. Every star you see is just one of hundreds of billions in our galaxy. And beyond that, trillions of galaxies filled with even more stars and planets. So here's the question. Where is everybody? This is the Fermi Paradox. The mind-bending contradiction between the overwhelming probability that alien civilizations should exist and the complete lack of any evidence that they do. Let's do some quick math. Our galaxy alone has around 400 billion stars, and we now know that most of them have planets. Even if just 1% of those stars had Earth-like planets, that would still be 4 billion potentially habitable worlds in our galaxy alone. Now let's be conservative and assume only 1 in a million of those planets actually develops intelligent life. That still leaves us with 4,000 intelligent civilizations in the Milky Way. And if just a handful of them had figured out interstellar travel, they could have spread across the galaxy in just a few million years. A blink of an eye on cosmic timescales. So again, where is everybody? There are only two options. Either alien life is rare, or something is stopping it from making contact. And neither answer is comforting. 1. We are the first maybe intelligent life is incredibly rare, and we're the first civilization to emerge. But if that's true, it means the universe has been waiting 13.8 billion years for us to arrive, which seems unlikely. After all, if the conditions for life existed billions of years ago, why wouldn't some other civilization have already taken over the galaxy by now? 2. They're out there, but silent. Maybe advanced civilizations are common, but they're choosing to stay quiet. One explanation for this is called the dark forest hypothesis. The idea is that the universe is like a dark forest, full of hunters. The smartest civilizations know that broadcasting their existence is a bad idea, because if someone's listening, they might not be friendly. Think about what happens here on Earth. When advanced civilizations encountered less advanced ones in history, like when Europeans arrived in the Americas, it often ended in disaster for the less advanced group. If an alien civilization is millions of years ahead of us, how would they see us? As equals or as ants? Maybe intelligent life exists, but it knows better than to make noise. 3. The Great Filter. This is the most terrifying idea of all. Maybe the reason we don't see aliens is that something wipes out civilizations before they get far enough to explore the galaxy. This great filter could be anything: nuclear war, artificial intelligence, climate collapse, or some unknown cosmic disaster. And the big question is, have we already passed it? Or is it still ahead of us? If it's behind us, that means life is rare, and we're one of the lucky ones who made it. Maybe getting from simple life to intelligent civilizations is much harder than we think, and we're an anomaly in the universe. But if the great filter is ahead of us, then every advanced civilization before us has hit a wall it couldn't survive. Maybe every species that discovers nuclear power eventually destroys itself. Or maybe AI always turns on its creators. Or perhaps some natural event like gamma ray bursts wipes out civilizations before they ever get the chance to spread. And that means we might be next. Here's the real kicker. If we ever do find evidence of an advanced alien civilization, it might not be good news. If the great filter is behind us, it would explain the silence. But if we find ruins of an advanced species, dead civilizations scattered across the stars, it could mean that the universe has a built-in expiration date for intelligent life. Or worse, it might mean that something else is out there, something that ensures civilizations never make it too far. So, next time you look up at the stars, ask yourself, is the silence peaceful, or is it a warning? Imagine a tiny, supernatural being that can break one of the most fundamental laws of physics without using any energy at all. This is Maxwell's demon, a thought experiment so strange that it seemed to challenge the very foundations of thermodynamics. To understand the paradox, we need to talk about the second law of thermodynamics. It says that in any closed system, entropy, or disorder, always increases. In other words, heat naturally spreads out, things tend to break down over time, and energy differences always even out. If you put a hot object next to a cold one, heat flows from hot to cold until everything is the same temperature. That's just how the universe works, right? Well, maybe not. In 1867, the physicist James Clerk Maxwell imagined something that seemed to violate this law. Picture a box filled with gas molecules, split into two compartments. The left side is hot, the right side is cold. Normally, over time, the molecules would mix, and both sides would reach the same temperature. But now, Maxwell introduces a tiny demon, a creature sitting at a door between the two compartments. This demon doesn't add any energy to the system. Instead, it just watches the gas molecules and acts like a bouncer. Whenever a fast, hot molecule approaches from the right, the demon opens the door and lets it into the left side. Whenever a slow, cold molecule comes from the left, it lets it move to the right. Over time, the left side gets hotter and the right side gets colder. The system is becoming more ordered, not more disordered. The second law of thermodynamics says this should be impossible, but the demon makes it happen without using any energy. If this worked, it would mean free energy forever. The temperature difference between the two sides could be used to run an engine, generate power, and do work, all without ever needing fuel. This would be perpetual motion, something physicists say can't exist. It would mean we could cheat entropy itself, undoing the natural decay of energy in the universe. If Maxwell's demon were real, it could break one of the most fundamental laws of physics. So why doesn't this work? Well, for a long time, nobody knew. The paradox haunted physics for decades. Then, in the 20th century, scientists realized something. The demon has to store information. Every time it observes a molecule and decides whether to open the door, it has to keep track of what it knows, which molecules are fast and which are slow, and information storage has a cost. Eventually, the demon's memory fills up, and it has to erase old data to keep working. And erasing information produces heat, a discovery made by physicist Rolf Landauer in the 1960s. This extra heat restores the lost entropy, meaning the second law of thermodynamics still holds. The demon doesn't get away with anything. It just moves the cost somewhere else. Even though Maxwell's demon doesn't work the way Maxwell imagined, it led to a deeper understanding of the link between information and physics. Today, this idea is used in quantum computing, thermodynamics, and even black hole physics. Some scientists think information itself is a fundamental part of reality, just like space, time, and energy. So in the end, Maxwell's demon didn't destroy physics. It made physics even weirder. Here's a weird thought. Your friends probably have more friends than you do. At first, that sounds impossible. How can most people be less popular than their own friends? Wouldn't that mean that everyone is below average, which doesn't make sense? Well, it turns out this is not only true on average. It's a mathematical certainty, and it reveals something strange about the way social networks work. The friendship paradox was first discovered in 1991 by the sociologist Scott Feld. He found that, on average, most people's friends have more friends than they do. Why? It all comes down to how friendships are distributed. Think about it like this. A person with very few friends isn't going to appear in many people's social circles, but someone with hundreds of friends is going to show up in a lot of social circles. That means highly connected people are overrepresented in your friend group, making it seem like most people are more social than you are, even when they aren't. It's the same reason why celebrities seem to be everywhere. If someone is famous, millions of people follow them. But that doesn't mean they personally follow millions of people back. They are seen by more people than they see themselves. Imagine a school with 100 students. Most of them have around 5 friends, but a few extroverts have 50 or even 100 friends. Now, if you pick a random student, chances are they have a modest number of friends. But when they look at their friend group, they'll notice something strange. Most of their friends are the ones with tons of connections. So from their perspective, it seems like everyone else is more social than they are. But that's just because highly connected people show up in more networks. The friendship paradox doesn't just apply to social networks. It shows up everywhere. On Twitter, the people you follow are likely to have more followers than you do. If you go to the gym, you might think everyone there is stronger than you, because the most dedicated athletes are also the ones who are there the most. Even in dating apps, Most people are competing for a smaller group of highly desirable individuals, making it seem like there's less interest to go around. The psychological impact. Here's where it gets dark. Because of the friendship paradox, social media can make people feel worse about themselves. When you scroll through Instagram, you're mostly seeing the posts of highly connected, highly social people. They're traveling, partying, succeeding, and because they're more visible, it seems like everyone is doing better than you. But this is just an illusion created by network effects. You're not seeing a random sample of people. You're seeing the ones most likely to be seen. The friendship paradox is built into the math of networks, but understanding it can change the way you see the world. Next time you feel like you're falling behind, remember, you're comparing yourself to people who are designed to be more visible than you. The reality is most people are probably feeling the same way, looking around, wondering why everyone else seems to be doing better. But the truth is, they're not. Black holes are terrifying. Anything that crosses their event horizon is gone forever. Not even light can escape. But here's where things get weird. What happens to the information about the stuff that falls in? In physics, information is everything. If you burn a book, you might lose the words, but the atoms of paper, ink, and smoke still exist. In theory, if you had a powerful enough machine, you could reconstruct every word. But black holes don't seem to follow this rule. When something falls in, the information about it vanishes. And that's a problem. Because if information is truly lost, our entire understanding of physics collapses. According to Einstein's general relativity, black holes are one-way exits from the universe. Whatever falls in is crushed at the singularity, where gravity is infinite. From the outside, no trace of what went in remains. It's just a featureless, dark sphere. But quantum mechanics tells us that information can't be destroyed. Ever. If you lose information, you break the fundamental laws of quantum physics, and that means you break everything. Hawking's discovery. The information problem gets worse. In 1974, Stephen Hawking made things even weirder. He discovered that black holes aren't actually black. They slowly evaporate by emitting what's now called Hawking radiation. Over trillions of years, a black hole will lose energy and eventually disappear completely. But here's the catch. Hawking radiation is completely random. It carries no information about what fell in, so when a black hole finally vanishes, the information is just gone. It's not hidden, not scrambled, erased from reality. This might not seem like a big deal, but it is. Physics is built on reversibility, meaning if you know the state of a system now, you should always be able to figure out what it was before. If black holes destroy information, cause and effect break down. The past could no longer be determined from the present, and that means the entire universe stops making sense. For decades, physicists have tried to solve the paradox. Here are some of the wildest ideas. Information is stored in the event horizon. Some theories suggest that instead of being lost, information is encoded in the surface of the black hole, like a hologram. This idea gave birth to the famous holographic principle, which suggests the entire universe might be a projection of information stored at its boundary. Wormholes and parallel universes. Some physicists think information might escape through wormholes, tunneling into another universe, meaning when black holes evaporate, the data might just go somewhere else. The universe doesn't care about information. A more radical idea suggests that maybe we're wrong about information conservation. Maybe the laws of quantum mechanics don't hold up in extreme conditions like black holes. If true, then everything we know about the fundamental structure of reality is incomplete. Some recent theories suggest black holes might have a firewall, a zone of intense energy at the event horizon that literally burns up anything that tries to pass through. But if that's true, it means general relativity is wrong, because it says crossing a black hole's event horizon should feel completely smooth. Physicists still don't know the full answer, but one of the most promising ideas is black hole complementarity, which suggests that information both falls in and stays outside the black hole at the same time. It just depends on who's looking. This plays into the deeper mystery of quantum physics, that reality might not be as solid as it seems. If we ever solve the black hole information paradox, we won't just understand black holes. We might unlock a deeper theory of everything, one that finally unites quantum mechanics and gravity, and that would rewrite the laws of physics as we know them. Imagine someone tells you, "I am lying." Seems simple, right? But now, think about it. If they're telling the truth, then they must be lying, because they said so. But if they're lying, that means they're actually telling the truth. So, which is it? This is the liar paradox, and it's one of the oldest and most disturbing paradoxes in philosophy and logic. A single sentence that should have a truth value, true or false, but somehow it refuses to fit into either category. And here's why that's terrifying. If logic can break this easily, then what else might be broken? The liar paradox isn't just wordplay. It shakes the foundations of truth itself. In classical logic, every statement is either true or false. But the liar paradox refuses to play by those rules. It oscillates, flipping between true and false in an endless loop. If logic had a self-destruct button, this paradox would be it. You might think, okay, this is weird, but does it actually matter? Yes, it does. This paradox exposes a deep flaw in how we define truth. In the early 20th century, logician Kurt Gödel used similar ideas to prove his incompleteness theorems, which showed that some true statements in mathematics can never be proven. That's right. There are facts about numbers that exist but can never be logically verified. The liar paradox hints at this kind of logical black hole, a place where the system of truth itself collapses. If you give a naive AI the liar paradox, it can get stuck in an infinite loop, constantly flipping between true and false. This actually happens in programming. When computers encounter a form of self-referential contradiction, they can get trapped in logic loops that crash the system. Some AI models even struggle with paradoxes, revealing the limitations of machine reasoning. If truth can break a computer, what does that say about truth itself? People have tried to fix this paradox for centuries. Some say the sentence is simply meaningless, but that feels like a cop-out. Others suggest there's a third truth value, something beyond just true or false. One approach is Tarski's hierarchy, which suggests that truth can only be defined from outside a system. In other words, you can never fully understand truth from within the system you're in, which, if true, has some deep implications about reality itself. If we can't fully define truth in language, logic, or even mathematics, how can we ever be certain of anything? And if self-referential paradoxes exist in logic, could they exist in the universe itself? Could reality have glitches, contradictions that can't be resolved? The liar paradox isn't just a puzzle. It's a crack in the very foundation of knowledge. And maybe, just maybe, it's telling us that some truths will always be beyond our reach. Imagine you're in a race. You're running towards the finish line, but before you can reach it, you have to get halfway there first. Then, before you can reach that halfway point, you have to cover half of that distance, and so on. If this continues forever, you're stuck performing an infinite number of steps in a finite amount of time. So how do you ever reach the finish line? Welcome to Zeno's Paradoxes, a collection of ancient puzzles that suggest motion itself might be impossible. The Achilles and the Tortoise Paradox. Take a simple race between Achilles, the fastest warrior in ancient Greece, and a slow-moving tortoise. To be fair, Achilles gives the tortoise a small head start. But here's the problem. By the time Achilles reaches the tortoise's original position, the tortoise has moved slightly ahead. And by the time Achilles reaches that new position, the tortoise has inched forward again. No matter how fast Achilles runs, he always has to catch up to a new position. The race should be easy for him, yet Zeno's logic suggests he never actually overtakes the tortoise. So, what's going on? At first, Zeno's reasoning seems absurd. Obviously, in the real world, Achilles wins easily. But the paradox isn't about running. It's about how we define motion. The problem is that we're dividing space and time into infinitely smaller pieces. The paradox seems to suggest that to move at all, we'd have to complete an infinite sequence of steps first. And if that's true, then why does motion even exist? If Zeno is right, then our entire understanding of reality is flawed. We experience motion, but mathematically it seems impossible. For centuries, people wrestled with this paradox. Some thought motion was just an illusion. Others believed something was deeply wrong with how we conceptualize time. Then, calculus arrived. In the 17th century, Isaac Newton and Gottfried Wilhelm Leibniz developed calculus, a tool for handling infinite sums. It showed that an infinite series can still have a finite sum. In other words, infinity doesn't necessarily mean impossible. Sometimes it just means really, really small numbers adding up. Achilles does, in fact, reach the tortoise because the infinite steps he takes get smaller and smaller, converging to a finite time. Even with calculus, Zeno's paradoxes still raise deep questions about the nature of reality. Is time truly continuous, or is it made of indivisible frames, like a film strip? If space is infinitely divisible, does that mean we're made of an infinite number of parts? And if motion only works because of calculus, does that mean reality itself is mathematical? The fact that we can resolve the paradox with math is reassuring, but it also raises an even bigger mystery. Did we just explain motion? Or did we just prove that the universe itself runs on equations? What if I told you that everything you've ever seen, heard, or felt your entire life could be an illusion? Not in a metaphorical way. I mean literally. What if you were nothing more than a brain in a vat, kept alive by wires, fed electrical signals that perfectly mimic reality? How would you ever know? The brain in a vat hypothesis is a modern version of an old problem. In the 17th century, the philosopher René Descartes wondered whether an evil demon could be deceiving him, fabricating an entire world around him. Today, we swap the demon for advanced technology, but the problem remains the same. If a brain in a vat is stimulated in the right way, it would experience a full, rich, detailed world, just like the one you're experiencing right now. The brain wouldn't know it's floating in a tank. It would think it has a body, friends, memories, everything. Now ask yourself, how do you know you're not that brain? The terrifying part is that there's no clear way to disprove it. Any test you could perform, touching something, feeling pain, even questioning reality, could itself be part of the illusion. Even if you say, "But my thoughts are real." That's exactly what a brain in a vat would think. This idea isn't just a philosophical exercise, it connects directly to the simulation hypothesis, the argument that our universe might be an artificial simulation running on some advanced computer. Think about it. If technology continues advancing, Humans might eventually create simulations so detailed that the people inside them believe they're real. If that's possible, then logically, there could be millions or even billions of simulated realities, but only one real one. So statistically speaking, the odds that you are in the real one, not great. Here's where things get really weird. Even if you are a brain in a vat or living in a simulation, would it change anything? If your experiences feel real, if your emotions are real, if the people you love feel real, does it matter whether they actually exist in some external sense? Maybe reality isn't about what's out there. Maybe it's just about the experiences you have inside your own mind. Still, next time you close your eyes and think about reality, you might find yourself wondering, is any of this actually real? Imagine you have a heap of sand, a real pile. Now, take away one grain. It's still a heap, right? Take away another. Still a heap. Keep going, one grain at a time. At what point does it stop being a heap? When there's only 10 grains left? 5? 1? And here's the real question. Was there ever a precise moment when the heap stopped being a heap? This is the Sorites Paradox, also known as the paradox of the heap, and it's a nightmare for logic. At first, this might seem like just a weird word game. But the problem goes far beyond sand. Think about baldness. If someone loses one hair, they're not bald. But if they keep losing hairs, at what point do they become bald or aging? You don't suddenly become old in one instant. So, when do you cross the line from young to old, or even identity? Every cell in your body gets replaced over time. In 7 years, almost none of your current atoms will remain. So, are you still the same person? The Sorites Paradox exposes a hidden weakness in how we define things. Where do you draw the line between one category and another? One radical solution to the paradox is mereological nihilism, the idea that objects like heaps, chairs, and even people don't really exist. According to mereological nihilism, all that exists are fundamental particles, tiny things like quarks and electrons. Everything else is just a convenient fiction we invent to make sense of the world. Think about a car. You can take off a tire and it's still a car. Remove the engine, and maybe it's kind of still a car. Keep removing parts, and at some point it's just a pile of scrap. But when exactly did it stop being a car? A nihilist would say, there was never a car to begin with. There were just atoms arranged in a way that we called a car, but the car itself was just an illusion, a label we placed on a bunch of separate pieces. The same applies to a heap of sand, or a human body, or a society. By this logic, the Sorites Paradox isn't a paradox at all. It's just exposing the fact that our everyday objects don't really exist in any deep way. Only the smallest, indivisible parts of reality do. The Sorites Paradox isn't just about sand, it's about the limits of human thinking. It forces us to ask, do our words and concepts really describe reality? Or are they just a convenient way for our brains to simplify a universe that doesn't actually have clear boundaries? And if that's true, then maybe nothing we think of as a thing really exists. Imagine a being that is truly all-powerful. It can do anything, control everything, rewrite the laws of physics on a whim. Now, here's the problem. Can this being create a rock so heavy that even it cannot lift it? If it can create the rock, then there's something it can't do. Lift it. If it can lift it, then it failed to create a truly unliftable rock. Either way, there's something this being cannot do, meaning it's not truly omnipotent. This is the Omnipotence Paradox, a problem that has haunted philosophers, theologians, and logicians for centuries. At its core, the Omnipotence Paradox asks, can unlimited power contradict itself? If an all-powerful being can do anything, does that include making itself powerless? Can it erase itself from existence? Can it create a rule it cannot break? Or what about logic itself? Can an omnipotent being make 2 + 2 = 5? Can it create a square circle? If it can, then logic is meaningless. Anything can be true and false at the same time. If it can't, then even an omnipotent being is still bound by logic, meaning its power isn't truly limitless. Philosophers and theologians have tried to escape the paradox in different ways. One approach is to redefine omnipotence. Maybe all-powerful doesn't mean able to do the logically impossible. It just means having all possible power. In this case, an omnipotent being wouldn't be expected to make contradictions real because contradictions are meaningless to begin with. Another escape is the idea that logic itself is created by the omnipotent being. Maybe the rules of reality, cause and effect, numbers, even contradiction itself are just constructs, and a truly unlimited being could rewrite them at will. But then we're left with a disturbing question. Why is logic the way it is? Could it have been different? The Omnipotence Paradox isn't just about theology. It's about the fundamental limits of power, logic, and existence itself. It forces us to ask, are there absolute truths even beyond the reach of ultimate power? If logic itself cannot be broken, then even the most powerful entity imaginable would still be trapped, not by anything external, but by the very nature of reality. Or even wilder, what if there is no such thing as omnipotence? What if the idea of unlimited power is itself an illusion? Something that can never exist in any logically consistent universe? And if that's true, then maybe the ultimate limit isn't strength or knowledge, but the inescapable nature of logic itself. In the early 20th century, mathematics was supposed to be on the verge of perfection. It was seen as a flawless, logical system, free of contradictions. But then, in 1901, one paradox broke everything. This is Russell's paradox, a seemingly simple question that shattered the foundations of set theory, the very language of mathematics. To understand it, imagine a village with a very peculiar rule. There is one barber. He shaves everyone who does not shave themselves. And he does not shave anyone who shaves themselves. Now ask yourself, does the barber shave himself? If he does, that means he's shaving someone who shaves themselves, which breaks the rule. If he doesn't, that means he's supposed to shave everyone who doesn't shave themselves, which means he must shave himself. It's an impossible loop. The rules collapse on themselves. Now replace the barber with mathematics itself, and you have Russell's paradox. At the time, mathematicians believed that any collection of things, numbers, objects, even ideas, could be grouped into a set. There was even a bold assumption. Any well-defined collection of objects should form a set. Seems reasonable, right? But then Bertrand Russell asked a devastating question. What if we define a set that contains all sets that do not contain themselves? Call this the Russell set. Let's ask the same question as the barber. Does this set contain itself? If it does, then by definition it shouldn't, because it only contains sets that do not contain themselves. If it doesn't, then it should, because it contains all sets that do not contain themselves. Just like the barber paradox, the whole concept breaks apart. Russell's paradox wasn't just some weird puzzle. It undermined the entire foundation of set theory. At the time, mathematicians were trying to build all of mathematics from set theory. Numbers, geometry, algebra. Everything was supposed to emerge from sets. But now, there was a contradiction right at the core. If set theory allowed self-contradictory sets, then it wasn't a stable system. And if basic math was built on set theory, then suddenly, nothing could be trusted. To stop mathematics from collapsing, a new set of rules had to be created. Like Zermelo-Fraenkel's set theory, which carefully limits what kinds of sets can exist. Instead of saying, any well-defined collection is a set, modern set theory is much stricter. It avoids paradoxes by forbidding sets from being defined in ways that could lead to contradictions. But this raises a chilling thought. What if there are more paradoxes we just haven't discovered yet? Russell's paradox showed that even the most seemingly solid mathematical systems can contain hidden contradictions. And if the foundation of mathematics can crack once, who's to say it won't happen again?